In this outcome, we explore why atoms bond together at all, and the three great families of chemical bond: ionic, metallic, and covalent, along with the structures each one builds. Let's get started. So why do atoms bond in the first place? Fundamentally, because bonding lets them reach a lower, more stable energy state. Most atoms achieve this by getting a full outer shell, mimicking the nearest noble gas, an idea we call the octet rule, aiming for 8 outer electrons. Only the outer shell electrons, the valence electrons, take part. And there are 3 main ways they do it: ionic, covalent, and metallic bonding, with the type depending on which elements are involved. Some key vocabulary first. Valence electrons are the electrons in the outermost shell, the ones involved in bonding. The octet rule is the tendency of atoms to gain a full outer shell of 8 electrons. Electrostatic attraction is simply the force between opposite charges. An ion is a charged particle, formed when an atom loses or gains electrons. And a lattice is a regular, repeating 3-dimensional arrangement of particles. Before we draw any bonds, let's understand the dot-cross diagram. It shows only the outer shell electrons, the ones that matter for bonding. We draw one atom's electrons as dots and the others as crosses, but be clear, dots and crosses are identical electrons. The labels are purely there to track where each one came from. These diagrams let us see at a glance where electrons are transferred or shared. It's a model to picture bonding, not a literal photograph of the atom. Let's take ionic bonding first. It happens between a metal and a non-metal. The metal loses electrons and the non-metal gains them, so oppositely charged ions form and attract one another strongly. Take sodium and chlorine. Sodium goes to sodium plus an electron, and chlorine plus that electron goes to chloride. The bond itself is the electrostatic attraction between the sodium ion and the chloride ion, and both ions now enjoy a full, stable outer shell. Let's draw sodium chloride as a dot cross. Sodium is 2, 8, 1, so it has 1 outer electron, which we draw as a dot. Chlorine is 2, 8, 7, so 7 outer electrons drawn as crosses. Sodium transfers its single outer electron across to chlorine. Sodium becomes a sodium plus ion, its outer shell now empty, with the full 2, 8 core beneath. Chlorine gains that dot and becomes a chloride ion with 8 outer electrons, 7 crosses, and 1 dot. We draw each ion in square brackets with its charge outside, and since they combine 1 to 1, the formula is sodium chloride. Now magnesium oxide. Magnesium is 2, 8, 2, so 2 outer electrons. Oxygen is 2, 6, so 6 outer electrons. This time, magnesium transfers both of its outer electrons to a single oxygen atom. Magnesium becomes magnesium 2+, having lost 2, and oxygen becomes the oxide ion, O2-, having gained 2. The oxide ion's outer shell now shows 8 electrons, 6 crosses, and 2 dots. The charges are 2+ and 2-, so they balance 1 to 1, giving the formula magnesium oxide. And because those charges are doubled, magnesium oxide's bonding is stronger than sodium chloride's. Magnesium chloride is a nice twist. Magnesium must lose 2 electrons to become magnesium 2+. But each chlorine atom, 2, 8, 7, can only accept 1 electron to reach 8. So a single magnesium atom has to hand its electrons to 2 separate chlorine atoms, 1 dot going to each. That produces 2 chloride ions. Now the charges balance. 1 magnesium, 2+, paired with 2 chloride ions, each showing 8 outer electrons. And that's why the formula is magnesium chloride 2, MgCl2. Let's look at what ionic compounds are actually like. They have high melting and boiling points because that strong lattice takes a lot of energy to break apart. They're solids at room temperature, forming regular giant ionic lattices. They conduct electricity when molten or dissolved, but not when solid, because the ions have to be free to move to carry charge. They're often soluble in water, which is a polar solvent, and they're hard but brittle, shattering when the layers are forced to shift. Let's understand that brittleness properly. In the lattice, positive and negative ions alternate in a neat, regular pattern. If you strike the crystal, you push one whole layer of ions along. Suddenly, like charges line up next to like charges, positive against positive, negative against negative. The strong repulsion between those same charge ions splits the crystal apart. That's why ionic crystals cleave along flat planes and shatter, exactly what you see when a salt crystal is struck. Now, metallic bonding, found in metals and their alloys. The metal atoms lose their outer electrons to form positive cations. Those electrons become delocalized, free to move throughout the entire structure. So you get a regular lattice of cations sitting in a shared sea of electrons. The bond is the attraction between the positive cations and that sea of delocalized electrons. Sodium, for instance, is a lattice of sodium ions bathed in a sea of electrons. This model neatly explains what metals are like. They're good electrical conductors because the delocalized electrons can move and carry charge. They're good thermal conductors too, as those mobile electrons transfer energy efficiently. They're malleable and ductile, since layers of cations can slide over one another while the electron sea keeps everything held together. And they generally have high melting points, thanks to strong metallic bonding, which gets stronger still with more delocalized electrons and higher cation charge. Let's set ionic and metallic bonding side by side. Ionic bonding is between a metal and a non-metal, with electrons transferred, giving fixed ions in a lattice. It conducts only when molten or aqueous, and it's hard and brittle. Metallic bonding is in a metal or alloy, with electrons delocalized rather than transferred, giving cations in a sea of electrons. It conducts even as a solid, and it's malleable and ductile. The key difference is transferred electrons versus shared, mobile ones. Onto covalent bonding, which occurs between non-metal atoms. Instead of transferring electrons, the atoms share a pair. A single shared pair is one covalent bond, and both nuclei are attracted to that shared pair, which is what holds the atoms together. By sharing, each atom gets to count a full outer shell. In a dot-cross diagram, we show this by overlapping the outer shells of the two atoms, with the shared pair sitting in the overlap. Let's draw hydrogen and hydrogen chloride. Hydrogen has one outer electron and needs two for a full first shell. In a hydrogen molecule, the two atoms share one pair, one dot, and one cross sitting in the overlap. So each hydrogen now counts two electrons, a full shell. In hydrogen chloride, hydrogen with its one electron shares with chlorine, which has seven. One shared pair sits in the overlap, and chlorine keeps three lone pairs. The result? Hydrogen counts two electrons, chlorine counts 8, and the formula is HCl. Now water and carbon dioxide. Oxygen is 2, 6, so it needs two more electrons, and each hydrogen provides one. Water, therefore, has two oxygen-hydrogen single bonds, plus two lone pairs left on the oxygen. Oxygen's outer shell shows 8, 4 shared in bonds, and 4 in lone pairs. Carbon dioxide is different. Carbon is 2, 4, needing 4 electrons, and each oxygen needs 2. So carbon forms 2 double bonds, one to each oxygen, written O double bond C double bond O, with each atom reaching a full 8. Let's tackle the nitrogen molecule. Each nitrogen atom is 2, 5, so it has 5 outer electrons and needs 3 more. The two atoms share 3 pairs of electrons between them, which makes a triple bond, written N triple bond N. 6 electrons, 3 shared pairs, sit in the overlap region. On top of that, each nitrogen keeps 1 lone pair, so both reach a full octet of 8. That very strong triple bond is exactly why nitrogen gas is so remarkably unreactive. There's a special kind of covalent bond worth knowing, the dative or coordinate bond. It's a covalent bond where both of the shared electrons come from just one of the atoms. For that, the donor atom needs a lone pair to give, and the acceptor atom needs an empty orbital to receive it. Once it's formed, it behaves exactly like any other covalent bond. We show it with an arrow pointing from donor to acceptor, and the classic example is the ammonium ion. Let's see how that dative bond forms when ammonia reacts with a hydrogen ion. Ammonia has 3 nitrogen-hydrogen bonds and 1 lone pair on the nitrogen. A hydrogen ion, H+, has no electrons at all and an empty orbital. Nitrogen donates its lone pair to form a 4th nitrogen-hydrogen bond. And because both electrons in that new bond came from the nitrogen, we draw it as an arrow from N to H. The result is the ammonium ion, with 4 nitrogen-hydrogen bonds, all identical once formed, and an overall charge of 1+. Let's define the covalent terms. A covalent bond is a shared pair of electrons between 2 atoms. A lone pair is an outer pair of electrons not used in bonding. A double or triple bond is 2 or 3 shared pairs between the same 2 atoms. A dative bond is a covalent bond where both electrons come from one atom. And delocalized electrons are electrons free to move through a whole structure, as in metals. Now some structures. Diamond is a giant covalent, or macromolecular structure made entirely of carbon. Each carbon forms 4 covalent bonds in a tetrahedral arrangement, and millions of these strong bonds link up into one continuous 3-dimensional network. That gives diamond a very high melting point, because so many strong bonds must be broken. It's extremely hard, which is why it's used in cutting and drilling tools. And it doesn't conduct electricity because there are no free electrons or ions. Contrast that with simple molecular structures. Here you have small molecules, held together internally by strong covalent bonds, but between the molecules there are only weak intermolecular forces. Think of hydrogen, oxygen, carbon dioxide, water, and iodine. These substances have low melting and boiling points because only those weak forces need to be overcome. They don't conduct electricity, as the molecules are neutral with no free charges. And crucially, melting them does not break the strong covalent bonds inside the molecules. Let's compare the 2 covalent structures directly. Diamond, a giant covalent structure, is one continuous 3-dimensional network with a very high melting point, extremely hard, non-conducting and insoluble in water. A simple molecular substance like carbon dioxide is made of separate small molecules with a low melting and boiling point, soft or gaseous, non-conducting, with only weak forces between the molecules. Same word, covalent, but wildly different materials depending on the structure. Here's a handy decision guide. A metal plus a non-metal gives ionic bonding. A non-metal plus a non-metal gives covalent bonding. A metal on its own gives metallic bonding. Then ask whether electrons are transferred or shared and decide the structure. a giant lattice, or simple molecules. And remember, it's that structure which ultimately explains the physical properties you actually observe. Let's check your understanding. First, why does an ionic compound conduct electricity when molten but not when solid? Second, can you draw a dot-cross diagram for the bonding in calcium fluoride, CaF2, and explain the ratio? And third, explain why sodium is malleable, using metallic bonding. Take your time with those.